Hi, and welcome to A-Level Stats Year 1, Chapter 7, Hypothesis Testing. Okay, this is widely regarded as like the hardest chapter. My advice with it is make sure you know the basic idea. Okay, I'll explain it as well as I go through it, but that tends to make it a lot easier, at least for me and for most people I've taught as well. Okay, the idea is, you assume a coin is, let's say you assume a coin is not biased, and we flip two heads in a row. Does that mean it's biased? Now you say probably not. The odds of that is only 1 over a quarter, or 1 over 2 squared. So it's probably not biased, probably just some bad luck, or good luck, depending on how you see it. We could then change the idea. What if I flip 3 heads in a row? 4 heads in a row? 4 heads in a row? 5 heads in a row? Or 10 heads in a row? At what point do you start to think, hang on now, maybe this coin is biased? Because the odds of getting 10 heads in a row is going to be 1 over 2 all to the power of 10, which is now 1 over 1,024. Okay? Just for context, that is less than 0.1%. So assuming at this point, there's probably a decent amount of evidence to suggest this coin is biased, is not going to be fair. And that is the whole idea of hypothesis testing. You've got some idea, whether it's an unfair coin, whether it's some sort of medical drug that has a special effect, and you want to say, what does the evidence say? And basically, how sure can you be that the coin is biased, or is it just bad luck, or really, really, really bad luck in this case? That's the basic idea. That's what you should get your head around. That's what you are doing. So every question kind of runs the same way. You basically have 4 steps. You're given some sort of hypothesis. In this case, the coin flips more heads than tails. You were also always given some data to test. I flipped 20 coins, I got 18 heads, for example. You then have 2 options. Either the hypothesis was true, okay? The coin does indeed flip more heads than tails. This is called the alternative hypothesis, which I cannot spell apparently. And we've also got another option, that it was just bad luck. Okay, like say the odds that happened was 10%, well then, that's probably just bad luck. It's probably not a biased coin. You just got a wee bit unlucky and you've gone a bit panicky. When it's just bad luck, we call that the null hypothesis. That basically means nothing's changed, nothing is new. Okay? To help you with this, you are always given an error interval. Okay? This quantifies how much bad luck you are allowed. So it might say test at an error interval of 5%. That means if the odd of it occurring by pure random chance, i.e. bad luck, was more than 5%, you'd go for the null hypothesis. If the odds of it occurring by random chance was less than 5%, so like 2.5%, you would then assume it was biased and therefore go to the alternative hypothesis. Also, while I'm here, these have special notations for H0 and H1, which does come up quite a lot in some questions, and you're expected to know them. Lastly, you've done that. You've tested your error interval. You either had bad luck or it is actually biased according to that error interval. And from this, we conclude whether or not the hypothesis is true. For all exam questions, you must say at the end some sort of sentence explaining this. We have done the maths. The odds of this occurring was 3.2%. That was less than our error interval of 5%. Therefore, we accept the alternative hypothesis. You must always say a sentence like that at the end of each question. And it's basically always the last mark to get. Okay, in real life, this is actually used quite a lot. The best way I could see was when they discover new particles. Okay, so here they said, we don't exist for certainty. We have done this hypothesis testing, and the odds of it just being bad luck was roughly 1 in 550 million. Okay, and that's basically how they work out most science discoveries now. Let's see a question, okay? So here, I've got a 10-sided dice, and I believe it rolls too many 3s. So I roll it 50 times, and I get 7 3s. We then want to test at a 5% error interval whether my hypothesis is correct, whether this dice is biased, or it's just bad luck. You're going to get more one number than another. That could happen. Key point. Because we have got 7 3s, you must always test that you have 7 or more. It must always be that number or more. Okay? It's not a hard and fast reason. The best way I can think about explaining it is, say you did like 100 trials, and you could have any possible number from 1 through to 100. If you just test the odds of that particular number, the odds of getting any number would always be really small. So for example, I could flip 100 coins and get 51 heads, and the odds of getting exactly 51 heads is really, really small, because there's so many numbers it could possibly be. So you always guess that number and more, or that number and less. So for this question, I want to work out the odds of getting 7 or more threes. Again, it's 7 or more, because I'm worried about getting too many threes. So I'm working out the odds that x is greater than or equal to 7. Let's define it as well. This is going to be binomial, because it's either success or failure. We have 50 trials, and the odds of getting any number should be, if the dice is not biased, 0.1. So here, you always put in the probability that you expect it to be, or that it should be if it was fair. Let's go to our calculators. I'll do this on the big calculators, and let's work that out. So we need to go to Menu, Stats, Distributions, Binomial, Cumulative, or using Variable. So we want to work out the odds of getting 7 or more. So lowest can be 7. We've got 50 trials, so most threes we get could be 50. And the odds of each success is 0.1. So the odds of that was 0.229 or 0.230 if I round. This most certainly is not less than 5%, so therefore we assume it is not biased. Okay, and we would have to write something like that. So the odds of getting 7 or more threes is around 23%, which is not in our error interval. So we accept the null hypothesis that the probability is 0.1. So basically we're rejecting the alternative. We're rejecting that the probability could be greater than 0.1. Okay, and that's the basic idea. Again, remember, every single question you should finish with this kind of sentence. I know it's a tiny bit boring, but it's what you're going to expect to see, and it's worth it to get that mark. Let's see the other side of the question. So here, the exact same setup, the exact same dice, exact same rolls. But here I'm suggesting that I'm getting too few threes now. I'm not getting enough. Okay? I've done my test, and I got 1 3 out of 50 rolls. And I'm going to do the same test to work out whether this hypothesis is correct. So here we work out the probability of getting not 6 or less, of getting 1 or less threes. So again, it's always that number you worked out. And here, because we had too few threes, we now want 1 or less. So basically, if we've got too few of a number, we always go for less. If we're getting too many, we always go for that number or more. Okay, so those things always go together. So we want to work out the probability that x is less than or equal to 1. We have the same binomial distribution as before, 50 trials, a success of 0.1. And again, let's go to our calculator. So the lowest I could have is 0, the most I can have is 1, 50 trials, the rest hasn't changed. The odds of this is 0.0337, 3p8. So that equals 0.0338 when we round. And this is actually less than 5%, because 5% is 0.05. So here we are within the error interval. So now we would say the probability of getting 1 or less threes is 3.38%, which is within our error interval. Therefore, there is evidence to reject the null hypothesis and accept the alternative hypothesis that P is indeed greater than 0.1. Sorry, less than 0.1, so we're getting less than what you'd expect. Again, you always need that kind of sentence. Just some extra maths that I should have written at some point for both these questions actually. Often you are told in each question to state the null hypothesis and the alternative hypothesis. So I'm going to do both of those now, even though I should do that at the start of the question, not the end. So the null hypothesis was nothing's changed. It's basically boring, for lack of a better word. So with the null hypothesis, its probability is 0.1. Again, if it's bad luck, that was probability. We just had some bad luck that made it look like maybe it wasn't. The alternative hypothesis is what's kind of been suggested in the question. we're suggesting we're getting too few threes. So for the alternative, this probability is actually less than 0.1. And from the previous question, we had too many threes. This would change to a greater than sign. So we had too many threes in that question. Okay, that's the example. You have two types of questions. I'm going to look at this one now. So back to our first question, we've got too many threes. I'm now going to actually ask you how many threes do I have to roll before I can satisfy this error interval. Okay, so I'm not going to write an alternative, I'm just going to work it out. We know the odds of guessing greater than or equal to some number has to be less than 5%, has to be less than 0.05. For this, out and away, the best way of doing it is going to be trial and error. Okay, so let's go back here. We had a lower of 6, let's change my lower to 7, see if that works. The upper is 50, because I want 7 or more, so 7 up to 50. And the odds of that is 0.229, nowhere near. Let's jump a bit, let's say if we had 10. Here we've got 0.02, which is 2.5%. I've possibly gone too far. Let's change my lower to 9. And that again is too far the other way. That's now big above 5%, so I was actually right last time that it should have been 10. And for our working out, we're going to write this down. We're going to say the probability of x being greater than or equal to 10 is 0. That number, 0.245. Okay, and again, therefore, you need at least 10 threes to satisfy the error interval. Often in questions, it'll ask you to work it out, and it will then say for like a 1-mark question, state the real error interval. In this case, because this was the first value less than 0.05, our real error interval is actually 2.45%. Okay, that's a very common thing to do. Last thing to explain, some definitions first. So key definitions, I should go through them all. These two I've already explained. Null hypothesis, nothing has changed. Basically, it was just bad luck. Alternative hypothesis is it was actually biased, it's actually making a difference, it's not where we expect it to be. Significance level, that's how much bad luck we're allowed. So again, 5%, 2%, 1%, could be anything really. Two more definitions I haven't mentioned yet. The first is the critical region. So from our previous question, this here was our critical region. If we got 10 or more threes, we would then, within the significance level, we then had a biased dice. So it's all values which are going to fall within the significance level. We then have a critical value. Here the critical value was the first value of that significance level. So my critical value was 10 here. So that was the important value. That was the tipping point from being fair but bad luck to being probably biased. Okay, those definitions you need to know, and they're referred to quite a lot in the questions. Lastly, to explain, we have two types of question. We have a one-tailed test and a two-tailed test. These are normally telegraphed fairly well in the exam questions. I'll explain them both anyway. If you had a one-tailed test, we kind of know what to expect. So for my example here, a new dog food is supposed to encourage dogs to eat more slowly. Yada 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 yada, test at 5% error interval. So here, because we know we want to eat more slowly, if they suddenly start eating a lot more fast, we don't care. That's not part of this question. Okay, we're told what to expect. Again, going back to my previous example, I always told you whether we had too many or too few threes. Okay, that made it a one-tailed test. You were told what to expect. That is in contrast to a two-tailed test. So here, a new herb is discovered in the Amazon and is believed to have an effect on blood pressure. Test at 5% error interval. Here we don't know what effect it has. And for the purposes of this question, we actually don't care. Like, if it increases blood pressure or decreases it, that's still going to be valuable for some part of medicine. Okay? In this case, you would have to split this 5% in half. You would basically test 2.5% at the really, really low end and 2.5% at the really, really high end. Okay, and I'll explain that more when I go through some exam questions in a second. So look for each question and make sure you realise if it's one-tailed or two-tailed. Normally they will tell you in the question, but not always. Okay, I'm going to go through two examples. Example 1, a student takes a multiple choice test. The test is made of 10 questions, each with 5 possible answers. That is fairly important. We'll get to that and get to why in a second. The student gets 4 questions correct, and her teacher claims she was guessing the answers. Using a one-tailed test, so here they do tell us, test at the 5% level of significance whether or not there's evidence to reject the teacher's claim. State your hypothesis clearly. So first thing, our hypothesis. We have the null hypothesis. That is called H0. In this case, we're assuming the teacher is right, that she is just guessing. If there's 5 possible answers, the odds of getting a question right at random is 0.2. The alternative hypothesis was she wasn't guessing. So that would be called H1. And that's going to say her odds of getting something right was greater than 0.2, greater than the chance of just randomly guessing. Okay, that's our first part done. We've stated our hypothesis. We now need to do some actual maths. So here we've got a binomial distribution. There are 10 questions. The odds of getting each one right in theory at random is 0.2 or 1/5. We know the student got 4 questions correct. So we want to work out what is the odds that she would get at least 4 questions right. Again, because we have the alternative hypothesis being p is greater than 0.2, that means that x is greater than or equal to 4. If this was less than sign, then so would this. These signs will always match, ignoring the equals part. Let's work it out. That is super fast because we have our calculators. So my lower is going to be 4. My upper is 10 because there are only 10 questions. And the odds of each success is going to be 0.2. That gives me 0.121 if I round. And if that helps, that is 12.1%. We had a 5% level of significance. So because this is greater than that, we do not have enough evidence to reject the null hypothesis. So all we need to do now is just say that, and we have a bunch of marks. So because the probability of getting at least 4 questions right is 12.1%, which is not within the error interval, or not within the level of significance. That means there is not enough evidence to reject H0 or our null hypothesis. Therefore, we can assume the teacher's claim, we can assume she is guessing. Or actually more precise than that. Therefore, there is not enough evidence to suggest she is not guessing. Okay, I doubt it'll make a difference, but that is a powerful distinction between those two things. You know, she got 40% right, which is a lot higher than 20%. However, it wasn't high enough to be sure within 5% level of significance that she wasn't just guessing. So I had to word it fairly carefully there. Okay, that's our first example done. Example 2, we have some wallpaper being manufactured. These questions are often quite thrilling. We know a defect occurs randomly at a rate of 1 every 8 meters of wallpaper. Okay, sorry, realised that question was slightly harder than I meant it to be. I wasn't actually binomial, so I've just rewritten it. Let's read this question instead. Jeff believes a coin is biased. He's going to flip it 50 times to see how many heads he gets and test his results at the 5% significance level. Part A, work out the critical region. So this question is two-tailed. The reason is he just says his coin is biased. He doesn't say whether he thinks he's going to get too many heads or too few heads. And then here it tells us actually, and it says make sure the value in each tail is less than 2.5%. So again, we're going to halve this when we go down to here, because half it goes to the top, half goes to the bottom. So let's work that out. We know this is going to be binomial, because each coin flip is independent. Here's got 50 trials, and we're going to assume the odds of getting heads is 0.5. Okay, and while we're at it, we can state our null hypothesis. So our null hypothesis states that the probability is 0.5, And the alternative hypothesis, that states that the probability is not 0.5. Okay, and this is another way to tell us something's one or two-tailed. If it's one-tailed, we'll be told greater than less than. If it's two-tailed, it's just not that number. It could be any other number, but just not 0.5. Okay, let's work it out. I'm going to test the low half. So I'm going to say too few heads. So I want the probability that I get less than X heads, and that has to be less than 2.5%, so 0.025. Then we go straight to my calculator. Let us guess that I need, we'll say 20 first. So sorry, my lowest should be 0. So anywhere from 0 to 20 heads I can have. I have a total of 50 trials, and the odds of success is 0.5. That's not enough. That is 10%, and I wanted 2.5%. So let's say the uppest it can be is 18. Nearly. That's 3.2%. 17. There we go. So let's copy that down. So 0.0164. So probability that I got 17 or less was 0.0164. So that's our first half done. We then need to do the exact same thing. We want to go on this side. I want to look at how many ways could we get too many heads. So here I want the odds of guessing greater than X amount of heads, again to be less than 0.025. A quick aside, if you're using the other calculator, the one that's not quite as massive, for you want to instead do probability that X is less than X should be 0.975. Do a 1 minus it, and then you have to add on 1 to your answer. Because if you work out the odds of getting 16 or less, for example, you don't want 17 or more. Okay, on to this question. I'll use the big calculator for this. So let's assume it's symmetrical, so probably 33 is a good shout actually. The upper should be 50 and the rest doesn't change. And yeah, it is symmetrical. So that was 33 I said. So the odds of guessing greater than or equal to 33 was the exact same probability. Okay, this is fairly rare. Typically they have probability not being 0.5, and that'll make it asymmetrical. So it won't be the same numbers with the same probabilities. And by same numbers, I mean the same difference from 25, which is the average or the middle. Okay, that is basically part A done. We need to write a critical region. So a critical region is either saying X is less than or equal to 17, or, so it should be lowercase x, or if we get 33 or more heads. Okay? No, it is uppercase X. Okay, sorry, so many X's can get confusing. Hope you can sympathise with me there. Part B, the actual significance level. So our probabilities weren't 0.25 exactly. They were 0.0164, and it's the same for both of them. So we add those together. That is our actual significance level. Okay, so that's actually 3.28%. Then part C, Jeff gets 37 heads. What we conclude from this, C, we can conclude, and the key thing here is that we are in the critical region. So we'll say there is evidence to reject the null hypothesis, or H0, and accept H1, that the probability does not equal 0.5. Okay, you could go further and say it's probably greater than that, but we weren't asked about that, so we don't need to mention it at all. And that is it. I hope that makes sense. I hope the way these questions work makes sense. My advice is always keep in your head what you are trying to do. Okay? So in this question, all these questions are all about quantifying how much bad luck you can have and how much bad luck it would take for something to be true. Okay, all questions work the exact same way. The only difference is basically are you working out a region or are you testing the results, as you were in the previous question, and whether or not it is one or two tailed. Okay, in the description you have some questions to try. Good luck, and thanks for listening.